Hey Royals, I would like to do two examples from lesson 3.3, just so that we hear the language. In 3.3, we are learning how to solve exponential equations. And you should see in the lesson a quick review of solving linear equations by isolation and solving quadratic equations, probably by factoring or maybe by isolation by completing the square or the quadratic formula. Solving exponential equations, a bit of a different approach as well. Just like solving a quadratic, you use different skills than solving a linear equation. We shouldn't be surprised that there's different skills when solving an exponential equation. Our argument is that for two powers to be equal, if we can set their bases the same, then the exponents have to be the same. So our goal is to try to write both sides as a single power of a common base, if at all possible. The other thing that might not have been stressed in this lesson is that in grade 11, we should be able to solve some exponential equations. It takes us until advanced functions to be able to solve any exponential equation. So this isn't always possible. You're not always capable of writing both sides as a single power without the aid of technology. The examples that you will see, you should be able to. Now, finding a common base is a little different than finding a common denominator. Looking at like this power right here, which is a base of 81, and this power right here, which is a base of 127th, often students think about using a base of 9. And you can write 81 as a power of 9. It's the second power, but writing 127th as a power of 9 is a little bit harder. It takes just maybe a little bit of trial and error then to think of your common base is usually a little bit lower than what your common denominator would be. I can focus on maybe 81 and 27. If they're both multiples of 9, that means that they're multiples of 3. And upon closer inspection, they're both powers of 3. Let me make my goal then to write both of these as a power of 3. 81 is the fourth power of 3. And 127th, actually, let me take my time here. I'll do something a little bit slower than in the lesson. Let me just reciprocate that 127th so that now it's a power of 27. It's the negative first power of 27. Because I can always take another step here. On the left-hand side, I'll use my power of a power rule. I'll keep my base and I'll multiply my exponents. On the right-hand side, maybe I'll do the same thing. I'll keep the base of 27 and I'll multiply these exponents, distributing to there. Now, both sides are now a single power. They were actually from the start as well, but they don't have a common base. But I'm a little bit closer to getting a common base. I can write 27 as a power of 3. It is the third power of 3. And then let me stress something that's difficult to stress in the lesson. I expect you to show your reader both sides as a single power of a common base. We are not set to equate our exponents because right now the right-hand side is not a power of 3. The right-hand side is a power of 3 cubed. So show your reader the left-hand side is a power of 3 with an exponent of 4x. The right-hand side is a power of 3 with an exponent of, I guess, negative 3x minus 3. And then we don't have the mathematic tool that will drop this base. We're also definitely not dividing by 1, or sorry, dividing by 3. You can divide both sides by 3, but you don't want to. If you did 3 to the exponent 4x divided by 3 to the exponent 1, that would give you 3 to the exponent 4x minus 1. It wouldn't cancel the 3 and just give you 4x. Now this is more of a, logical argument. We say if 3 to the exponent 4x is equal to 3 to the exponent negative 3x minus 3, if these powers are equal and their bases are equal, then the exponents have to be equal. So we're solving a different equation. We're saying that the solution to this original equation will be the solutions to this equation. This is where we shift gears a little bit. I feel like I was using exponential strategies here. This is an exponential equation. The only way this exponential equation will be true is if the exponents are equal. So when I set the exponents equal, then I find myself solving a linear equation, and I shift gears into a grade 9 approach. I'm going to solve a linear equation by isolating. I undo operations with inverse operations. Those skills are still useful. They just won't help you. You can't really undo these operations here with inverse operations. It's a different type of equation. And there you go. Example B. Not much new to show here, other than the fact that our final equation isn't going to be a linear equation. Left-hand side isn't a single power yet. It's a power of a power. I'll use my power of a power rule. I'll keep my base and I'll multiply my exponents. Right-hand side, if I don't recognize it as a power of 2, I could count on my fingers or use even a dollar store calculator to verify how many factors of 2 I would need to get 64. You might want to become familiar with some of your powers of 2. And here's the argument. 2 to the exponent something equals 2 to the exponent something else. That means that something has to equal something else. Okay. Don't worry about what step you're showing here. You don't need to manipulate the equation. Each line here it's not the same equation. It's a different equation that hopefully has the same solution. Okay, now we will be given another opportunity to demonstrate we understand how to solve quadratic equations. I'm not going to try to set both sides to a single power of a common base. I'm not going to try to isolate x by adding 5x to both sides and then taking the square root, or dividing both sides by x. I am expected to know how to solve linear equations and exponential equations and quadratic equations. And I'm going to choose to solve this quadratic equation, probably not by isolating by completing the square. It's not a good candidate for that since 5 is odd. I'll set it equal to 0 so that I could use my quadratic formula if I want, but faster than the quadratic formula would be solving by factoring. I can look at factors of -6 that have a sum or a difference of -5. Let's try -6 and +1, and always check through distribution. Things look good. Then when I'm solving a quadratic equation by factoring, the argument is if something times something else is 0, then either something is equal to 0 or something else is equal to 0. I didn't really go out of my way in quadratics to put that word then here, but maybe I should have. Because again, I'm not solving the same equation. I'm solving two separate linear equations whose solutions should give me the solutions to this quadratic equation, whose solutions should give me the solutions to this exponential equation. So I start off with exponential skills, I shift to quadratic skills, and then I shift to linear skills. Really having an opportunity to demonstrate to any reader that I understand how to solve all three of these types of equations. Last thing I want to mention is that the final example, I believe it's labeled E, is usually considered extension. I believe those types of questions are labeled as extension in your homework. They are a little different. You can try them out and message me if you want to see a solution, but I doubt I'll be sharing it with the class because it's not quiz or test level.